To build such an A, we have to consider the group SL2C. What is it? SL2C, they are complex 2 times 2 matrices with unit determinant. Why? This is to build the matrices here, which are 2 times 2. So in total we have 4 by 4 matrix. A matrix A of SL. So special linear. SL means special linear instead of general linear. General linear means invertible only, and not with determinant 1 necessarily. And this is special linear. So it has this form, can be written as by means of the Pauli matrices and the identity, like this, where A is complex, A, B are complex, and can work out by the properties of the Pauli matrices the determinant should be 1. So this is the condition. Can also check that A to the minus 1 is just this. Now, a property that you can prove is that if you take the matrices sigma mu and transform them as follows. Now, well, one thing that we have not said about the matrices sigma mu is that they are Hermitian. As you can check. So if you consider this is Hermitian as well, and can be expanded in a basis of Hermitian matrices. Well, you can prove that that is a Lorentz transformation. And actually the property is that SL2C is the double cover of what? Of the SO13 plus, which is the special, or 31, depends if you want to write SO13 or 31. Which means the component, plus means the component of the Lorentz group that contains the identity. Because the Lorentz group has several components. Why double? Because you see here we need a relation from A, matrices A to lambda, and it will never be unique because anytime you find A minus A will also be good. So you cannot associate just one A to a matrix of SO plus 1, 3, but two. Aside from the details, we want now explicit formulas to use this, and we can build the transformation of fermions starting from this property. So we said that we want several things. We want this one, and before that we want this one or that one. Let's start from this one. So gamma 0, A dagger gamma 0 should be equal to A minus 1, but gamma 0 is this. Let us recall that A is parameterized like that, so dagger of that. Dagger 0, 1, 1, 0. That is equal to what? Well, when you multiply by gamma 0 a diagonal matrix, you just exchange the two blocks. And that should be equal to A to the minus 1 instead of A dagger. So A tilde to the minus 1, A minus 1 goes there. So from this you derive two properties that are the same, because A dagger equals A tilde to the minus 1, and from the other one A tilde dagger is equal to A to the minus 1, which is a consequence of that. So the two give the same condition, which relates A tilde and A. So A tilde is A dagger to the minus 1. To the minus 1. And since A was A sigma 0 plus B dot sigma, A dagger is what? Since the matrices are Hermitian, you just take the complex conjugate of the coefficients. And then it's a matrix of the same type, and when you do the minus 1, you just change this sign. Okay. Okay, and you can prove that A tilde dagger sigma tilde mu A tilde is equal to the same Lorentz transformation for the tilde with the matrices with tilde. Let us check this. This follows from the other property. should be straightforward, equal lambda mu nu rho sigma nu. If we complex conjugate this, you have the complex conjugate of everything. Okay. Dagger and complex conjugate is transpose. Sigma mu complex conjugate. A complex conjugate. Then you have lambda mu nu that is real, and that then you have here the complex conjugate. Now recall that if you multiply the matrices sigma, the conjugates of the matrices sigma by sigma 2 to the left and to the right, you get the tilde matrices. So let's multiply by sigma 2, sigma 2. And then you have sigma 2, A transpose sigma 2, sigma 2, sigma mu star sigma 2. Sigma 2 squared is -1, so I can insert sigma 2, sigma 2, and sigma 2, sigma 2. And then you have sigma 2 A star sigma 2, and that is lambda mu sigma 2 sigma star mu sigma 2. So that goes into the right identity if this is A tilde dagger. This is, we know, sigma tilde mu. This is A tilde, because then we have lambda mu nu sigma tilde nu. So we just need to show this actually, because the other one will be the same. A tilde is equal to sigma 2 A star sigma 2. A tilde equal to sigma 2 A star sigma 2. But what is A star? A star is A conjugate plus B conjugate, and then you have sigma 2 sigma conjugate. And that is yes, so let's do this. A star sigma 2 times sigma 2 is I said that sigma 2 times sigma 2 was -1. No, sigma 2 times sigma 2 is +1. Sigma 3 plus the squared of the matrices is equal to 1. So sigma 2 times sigma 2 is +1. So here you have A star sigma 0, and then you have B star sigma 2 sigma star sigma 2. That is sigma tilde, because when you have sigma tilde, but sigma tilde vector is minus sigma. I recall what sigma tilde is. Have to go back to sigma tilde is just minus sigma. And this is invariant. So you get A star sigma 0 minus B star sigma, and that is precisely what we wanted. So this is okay. So once we have the first property, you have also the second property, and that is what makes everything work, because now we can check that these two, this one and the one with no tildes, get the right transformation for the gamma matrices. We also have what we want, namely A minus 1 gamma mu A equals lambda mu nu gamma nu, which is oh yes, this is what we had before. We can multiply again by the inverse, turn it to the right hand side, and then you have lambda A to the minus 1 gamma mu A equal, when you multiply you have to switch the indices by the inverse, and so you get this. That is what we want. That is indeed the case after we build the matrix A like that, because A tilde to the minus 1 is what? So let's recall that sigma gamma mu is this, that A is this, and that A to the minus 1 will be this. And when you multiply that, you will have what? Well, let's multiply the first two, 0, A tilde minus 1 sigma mu, A minus 1 sigma tilde mu, and that is 0 this is a tilde also. Let's check, because there's something wrong here. So this times this is now 0. This times this, no. A tilde to the minus 1 there is something wrong here. Yes, there is something, well, not wrong, but we have to complete it. A tilde to the minus 1, A tilde to the minus 1, here it is A dagger. and this is a to the minus 1, so this is a dagger tilde. So it's better to organize this a little bit differently. Cut. So a dagger tilde. Let's multiply the last two first. So you have 0 sigma mu a sigma tilde mu a tilde 0. And now you have 0 a dagger sigma mu a dagger tilde sigma tilde mu a tilde. And now we use the properties we have seen, namely that this is lambda mu nu 0 sigma nu sigma tilde nu, and that is lambda mu nu gamma nu. Okay. So this works. We have to we need to do it for the coupling to gravity. We have to know the relation between lambda and a more explicitly. So let's write it down and prove it. The relation between lambda and a is as follows. Let us write lambda equal to the exponential of a matrix, some other matrix, which here is called rho. Let me see if better notation. A, B. Let me write it T. Don't like the notation here. So this is the exponential of the matrix. Then A is the exponential of sigma mu nu T nu. Yeah. So the change in the exponents of lambda and A is easy. The matrices are complicated. Where sigma mu nu is this matrix. It's minus 1 divided by 8 commutator of gamma mu, gamma nu. And gamma with lower index is just gamma with an index lowered by means of the flat space matrix. So basically A is e to the trace of sigma t, where the trace is understood to be in these indices only, because t has only these indices. But sigma has, there are many sigmas, so there are sigma mu nu, but for every mu and nu, sigma is a matrix in the indices of the gamma matrices. So, but the trace, like that, sigma t should be understood now from now on that when you mean this trace, we trace those indices and nothing else. And we have to prove that we have this. We have to prove this now. Now to prove that, so to prove this, we need a formula that is famous, so I think you will see it in other cases. We will not make the proof to the end, but just describe how it works. We need the Campbell-Baker-Hausdorff formula. What does that formula say? For every matrices A and B, we have the following identity. This thing is, let me write it like that, e to the adjoint, it's like an operator, adjoint of A is the following operator that takes the matrix B and commutes it with A. And so when you expand this exponential, you get commutators of commutators of commutators. So basically you have exponential is 1 plus x, e to the x, so 1 plus the commutator plus 1 divided by 2 factorial the commutator of the commutator and so on. And these are n commutators. You have to use this and another identity, but so you choose B equal gamma mu and A equal to minus the trace of sigma rho, because in that case e to the A is equal to A minus 1, e to the minus A is equal to curly A, so you have curly A gamma mu to the minus 1 curly A, which is this, that is equal to B plus all those commutators, so gamma mu plus the commutator with A, which will be, now we make it more explicit, B plus, then we will see that the rest, once we do the first, the rest is, we will not do it, but it is easy to do because it's always the same thing. Here, let's see what happens here. Sigma rho, sigma t, I call that t. Old notation here was rho, but I do not want to use it. It's confusing. It's better to use a capital letter here. So again, t has no indices besides the space-time ones, and so in this commutator, basically, so let's write this commutator minus trace of that sigma mu nu t mu, this is the trace, gamma, okay, we have to change names to the indices. So t goes out, and you have to compute that commutator. This commutator is known. So you have a commutator between sigma, sigma is a commutator of gamma matrices and the gamma matrix. And there is an identity that you can check. That is 1/2 eta mu rho gamma sigma minus eta mu sigma gamma rho. Basically, the commutator of these two objects is that, because it's like what we are proving basically is that these are generators of the Lorentz group. This is a vector. When you take a vector and apply a Lorentz transformation, you get a vector. All right. Just necessary if you want to check the coefficient in front, because necessarily this has to be a combination of gamma matrices. It has to be built like that. It has to be anti-symmetric and rho in sigma. So, for example, if you want to check this in a simple case, to check the coefficient, let's replace the definition of sigma, which is a commutator minus 1/8, and if we take mu equal rho, we get minus 1/8 gamma mu gamma sigma minus gamma sigma gamma mu commutator gamma mu. That is minus 1/8. Then you should remember some properties of the gamma matrices that we need. So yes, that see how much time we have. 51. Okay. So what is this? This is, you can anti-commute by means of the Dirac algebra, and then you have sigma mu. Another property is Yeah, mu equal rho actually means that we are multiplying. We are also raising and lowering some index. So is mu mu. This is mu and this is a delta then. And this is 4, that you can check. So minus 4 plus 2, that is minus 2 gamma sigma. So the first object is minus 2 gamma sigma. Then you have minus 4 gamma sigma. And then you have the minus that is another minus 4 gamma sigma, and then you have minus 2. So that is yes, 3, that is 12 divided by 8, 3 divided by 2 gamma sigma. On the other hand, it should be equal to that when mu is equal to rho, or you multiply by eta mu rho, you have 1/2 4 minus 1, 3. So that's okay. So let's insert it here and check what you get. You get that so a minus 1 gamma mu a that is gamma mu, and then you have this object here minus t nu rho and then this commutator rho nu gamma mu. So 1/2 rho nu gamma mu eta mu rho gamma nu minus rho nu. You have to exchange rho with nu, so that will be a delta because there is an eta mu rho gamma mu nu gamma rho. Let's check if everything is okay. Plus again, so that is gamma mu minus this is t mu nu gamma nu divided by 2 plus 1/2 t rho gamma rho, and that will be mu. Okay, plus, let me write it better, gamma mu. So here you have eta mu rho. So this is t gamma nu there is a nu there, and there is a mu. I have to write it like that. But anyway, a property that we didn't mention before, recall that lambda is e to the t. And the property of this matrix, which is the exponent of lambda, is that when you raise or lower its indices, it's anti-symmetric. It's like a rotation. So those two contributions that we have here are actually the same, and that's why you lose the coefficient 1/2. And so this is e to the t gamma up to the corrections. We have just checked the first order. Point is that to the other orders with the Campbell-Baker-Hausdorff you can repeat, because you will have that basically A is sigma and B is gamma, and the commutator of sigma is gamma, and gamma is a gamma. Here you have gamma, sigma, sigma, but the commutator of sigma and gamma is a gamma, and so you iteratively use always the same thing, and just check that the coefficients reproduce the exponential, but you see the coefficients are those of the exponential already there. Or if you want to, you can find out shortcuts to get to the right result, but in the end that's what you get. So that's the result. So to summarize, we have now done everything in flat space to build an action that is invariant. We have not much time left, but we just convert in these 2 minutes the indices, because everything we have said so far will be transferred from space-time indices mu nu to flat space indices. So we have this thing. We will use such gamma matrices. We will use Pauli matrices with those indices, sigma tilde A. We will define gamma A like that. Nothing with space-time indices we have seen so far will have space-time indices, because only in the basis of flat space indices we will have the gamma matrices equal to constants, because otherwise you should need to introduce not constant matrices, but matrices that depend on the point. We won't do it. So thanks to the field bank, we will be able to move all these objects into the tangent space, and the tangent space is just a vector space. It's the same space for every point, and therefore in that space every object there will be just the constant matrices we have been working with so far. And the range of transformations will be reduced from the general linear transformations which we were used to study so far, just to Lorentz transformations. So omega AB will be restricted to Lorentz transformations, because the Dirac action in gravity will be invariant under Lorentz transformation. Of course, it cannot be invariant under general linear transformations. Okay.